Hi guys, I'm Sai Krishna. So let us look at question number 1. In question number 1, we are given that x of t is a real WSS with autocorrelation as Rxx of tau and power density of spectral density as Rsxx of omega. We are asked to show that Rxx of tau is real and even in part A. So let us look at the solution for this. So in question number 1, part A, we have to show that autocorrelation of tau is real and even. So first let us show that Rxx of tau is real. So for this we know that Rxx of tau can be written as E of x of t plus tau x of t. In the given data, we are given that x of t is real WSS. So x of t as it is real and WSS real WSS. So the whole thing becomes real. So we have shown that Rxx of tau is real. Now let us show that Rxx of tau is even. So for this, let us again define what is Rxx of tau. We can write Rxx of tau as E of x of t plus tau of x of t into x of t, which can be written as Rxx of t plus tau comma t. This can also be written as E of x of t into x of t plus tau. So this can be written as, this equation can be written as Rxx of t comma t plus tau. So this is equal to Rxx of minus tau. So as Rxx of tau is equal to Rxx of minus tau, Rxx of tau is even, as tau is equal to minus tau. So hence Rxx of tau is both real from here and even from here. So in this way I have completed the part A. So let us look at the part B. So question number 1, part B. So here we are asked to show that the power spectral density Sxx of omega is even and non-negative. So we have to show that Xxx of omega is even and non-negative. So through the definition we can write power spectral density as integral from minus infinity to infinity Rxx of tau e to the power of minus j omega tau d tau. So from complex numbers we can write this as cos omega tau minus j sin omega tau. So let us substitute here. So this becomes minus omega to minus infinity to plus infinity Rxx of tau cos omega tau minus j sin omega tau d tau. So this is equal to integral minus infinity to infinity Rxx of tau cos omega tau d tau minus infinity to infinity Rxx of tau into j sin omega tau d tau. From the part A we have shown that Rxx of tau is even. So this part is even. We know that this the sin omega t function is odd, so the whole function becomes odd. Okay, as this is even function and this is also an even function, the whole this equation, this expression becomes even. So as this is odd, this integral becomes 0, and as this is even, this becomes 2 times of integral 0 to infinity Rxx of tau cos of omega tau d tau. So as cos omega tau is an even function, we can write this as 2 from 0 to infinity Rxx of tau cos of minus omega tau d tau. So the whole expression can be written as Sxx of minus omega. So as Sx of omega equal to of minus omega, this is an even function. So we have proved that Sxx of omega is even. So let us look at Sxx of omega is non-negative. So here let us take an example of h of h function where x of t is the input and y of t is the output. So h of omega, okay, so here h of omega is 1 when omega is greater than omega 1 and less than omega 2 and 0 otherwise. Now let us calculate e of y square of t mod. So we can write this as, this implies e of mod of y square of t is equal to integral minus infinity to infinity mod of h of omega square into Sxx of omega d omega. As this is bounded between omega 1 and omega 2 and the expression value is 1, we can substitute this as the integral omega 1 to omega 2 1 into Sxx of omega d omega. So we can clearly see that the area of this curve is greater than or equal to 0. Equal to 0 when both are equal, omega 1 and omega 2, greater than 0 when omega 2 is greater than omega 1. So we can write this as Sxx of omega is non-negative as well. Hence, from here we have shown that Sxx of omega is even. From here we have shown that Sxx of omega is non-negative. So Sxx of omega is both even, we have shown that it is both even and non-negative. So in this way we have proved that Sxx of tau is real and even, and Sxx of omega is even and negative. Thank you.